All right, here we go. Unit 2, Day 3, the power rule. By the end of today, you are going to be able to find the derivative of any polynomial function like that. Something like 5x cubed minus 4x squared plus 2x plus 7, you will have the derivative of that in under 5 seconds. That is compared to what we did as a rite of passage, which I will leave here just so you can see and appreciate this rule that we're about to learn, the limit definition of a derivative. The limit definition of a derivative takes like a page of work and really nasty algebra, and this is only for x squared, right? Like if there was an x cubed term in here, this would take 3 pages worth of work to really do out nicely. The only things I really want you to remember about the limit definition of a derivative, this is how calculus was discovered and invented, is thinking in terms of limits. People said, okay, I want to find how fast my function is moving at exactly -1. They said, well, I can't really tell that because I need 2 points for a slope. They said, but what if we wrote out a formula for slope and we took the limit as the change in x, which in this case is h, heads to 0. That's the limit definition of a derivative. They looked at the slope between the red and the green points, and then let's do I'll keep erasing these, then these 2 points, then these 2 points, then these 2, just getting closer and closer and closer until your secant line becomes a tangent line. That's the limit definition of a derivative. And it does work, right? So you do all this algebra out, you do your cancellations, you finally direct substitute, you get that f prime is 6x plus 2. And that's so powerful, right? Like what this tells us is, if I ask you, what's the slope of the tangent line when x is any point, all you do is you plug in to f prime of x equals 6x plus 2, and that will tell you what the slope of the tangent line is. As an example, the one we were talking about, if you plug -1 into the derivative, you get out 4. So we would say f prime of -1 equals -4. So the slope of the tangent line at -1, yeah, that looks about right. This looks like it's going to end up being down 4 over 1. Down 4 over 1. That is the slope of that red tangent line. And it's not just the slope of the tangent line. It's the instantaneous rate of change. It's how fast is my function changing for a tiny, tiny, tiny change in x, for an infinitesimally small change in x. So it's great. The limit definition works. It just takes pages and pages of work, and it's a rite of passage. You're through that rite of passage. Just don't forget these key points. Number 1, the way this was discovered, the derivative is the slope of the tangent line, and we reasoned through that we can find that slope by taking the limit of the secant line slope as one of our points gets closer and closer to the other. That secant line just collapses into a tangent line, and so that's where the derivative comes from. We're going to add on a couple new pieces of terminology here just so we can do the power rule effectively. So we already know a few things about the derivative: slope of the tangent line, instantaneous rate of change, f prime of x. I'm going to add one more here for you. It looks like this says d dx f of x. You'll hear me say that sometimes, d dx, but it's really sloppy. What this actually says is, it says the derivative, so you can imagine that this little d says the derivative of f of x with respect to x. The with respect to x part just means what is changing? What is my independent variable? What am I measuring change with respect to? So we would say, how fast is f of x changing relative to x at one moment in time? You put your speed gun on it. What is the rate of change at that one point in time? That is the derivative. We would say the derivative with respect to x of f of x. How fast is y changing relative to x? Again, it's not a fraction. It's just we say that out loud, the derivative with respect to x of f of x. So using that notation, we're going to do 4 motivating examples to build up to the power rule. First motivating example, it's the one on the left. The derivative with respect to x of 2, I'm just going to cross this out here because it's wrong. The derivative with respect to x of 2 is 0. How do I know that? Just like off the top of my head, I think, okay, derivative rate of change. Is 2 changing with respect to x? 2 doesn't care what x is. There's no x in that expression. The derivative of 2 is the slope of that flat line on the left. It's not changing. It's always 0. The derivative of 5, 0. The derivative of 1,000, 0. The derivative of 1,000,000, 0. The derivative of pi, 0, because pi is a number. The derivative of any constant number is just the slope of a horizontal line at some different place. So the derivative of a constant is 0. That's point number 1. The derivative of a constant number is 0. Now the one on the right, I had to fix that little typo. The derivative with respect to x of 2x minus 3 is 2. And how do I know that so fast? Well, it's a line. It has a y-intercept of -3 and a slope of 2. Up 2 over 1, up 2 over 1. The rate of change, every time x goes up 1, y goes up 2. And that doesn't change because it's a flat horizontal, or it is a straight line with a non-changing slope. So the second point here, the derivative of a straight line is just the slope of that line. So if I say what's the derivative of 5x, you'd say 5. What's the derivative of 3x? 3. What's the derivative of -0.5x? -0.5. The derivative of pi x? Pi. It's always just the coefficient there. Derivative of a number is 0. Derivative of a line is just the slope of that line. We're going to build on that. 2 more quick motivating examples. These ones are going to be a little trickier to see, so I'm just going to show, yes, they make sense. And so now instead, because these are trickier here, this isn't 2 separate examples. This is one example. This is one example of, what if I take this derivative and I plot it as a graph? So I take the derivative and I plot it. I plot a list of all of the slopes of this function. So I take x squared. I look at when x is 0, the slope of my tangent line, I'll do this one in purple, the slope of my tangent line, this purple horizontal line here, you can barely see it, well, that slope is 0. If this function here on the right in blue is the derivative of the one on the left, well, when x is 0, 2 times 0 should be 0, and it is. And we can do that for any point on the function. I'm just going to do 1 to save time. Let's go ahead and let's look at what happens when x is, let's go ahead and look at what happens when x is 2. If I try and really carefully draw this tangent line, I've done like not a good job. That's too shallow there. If I really try and do a good job drawing this tangent line, what we will see here is that this slope is 4. And if I look on my derivative function, 2 times 2 should be 4, and there it is, 2 comma 4. So the derivative of the parabola x squared is the line 2x. You can look up any point on this line, it tells you the slope of that parabola on the left at that point. The slope at -1 is -2. Does that check out? Yes. The slope at -1 of the tangent line is -2, so it checks out. Super quick, right? Same idea, x cubed, the derivative becomes 3x squared, and maybe you're starting to see the pattern here, but I'll just do 1 as an example here of how this works. When x is, let's say, 1, the slope of this tangent line, I'm so bad at drawing these, the slope of this tangent line, I always draw them too shallow, is 3. 1 comma 3. You plug in a 1 to the derivative, you get out 3. So it checks out. So the derivative of a cubic function is a squared function, a quadratic. So the key point I want us to take into starting the power rule, the derivative of a function, it's always going to go down 1 degree. If it was a sloped line with an x term, it goes to a flat line. If it was a parabola, the derivative is a line. If it was a cubic function, the derivative is a parabola. So you go down a level, and that's going to be the starting point for the power rule. Here's the power rule. If you remember one thing from calculus, 10 years from now, you're going to remember how to do the power rule, because it's fun, it makes these things go super fast, and it's super, super useful, and here it is. The derivative with respect to x of some polynomial, so x to a power or like a bunch of x to different powers in a row, polynomial, is n times x to the n minus 1. So what happens is you take this n, you multiply it by whatever is in front of the x, and you reduce the degree, you subtract 1 from the exponent. And so we'll do this step by step for a couple here. Let's say we do f prime of 3x squared minus 2x plus 3. One step at a time. We'll do first 3x squared. Our key point above was the derivative of a parabola should be a line. And by the power rule, that checks out. 2 times 3 is 6. X to the 2 minus 1, 6x to the first. Okay? Next, 2x. Let's do, we learned, so negative 2x, that's like a line with a slope of down 2. We learned that that derivative should be negative 2. The reason it works out is, remember, 2x is 2x to the first. So if you did this the power rule way, you'd have 2 times 1 is 2, x to the 0, anything to the 0 power is 1. That's why it's there. And finally, that plus 3, the derivative of 3 with respect to x is 0. The derivative of any constant is 0 because it's not changing with respect to x. So there it is. What would have taken a page of work, the derivative of 3x squared minus 2x plus 3, takes, I'm explaining this all, but it takes 5 seconds. So you can do one of these so quickly now. Let's say we had f prime of what's on the right. I'm going to show you like real speed now how you're going to be able to do it. 3 times negative 5, that's negative 15. X to the subtract 1 is x squared. Plus 4, that's 2 times 2. X to the first power, negative 3x becomes minus 3. That's it. That is the derivative. This tells you the slope of the tangent line at any point on that function. That's so cool, right? And this works for any one of these. If it's in a different order, it's fine. It works totally just the same. So we would have here the derivative of 6 is 0. The derivative of negative 3x cubed is negative 9x squared. The derivative of 6x to the fourth plus 24x to the third. And yeah, it's out of order, but that totally works. Doesn't matter whether it's a negative exponent. You just have to remember, if you're subtracting, we're getting more negative. So the derivative of negative 2x to the negative first, negative times a negative, is positive 2x. This is where people get messed up. Negative 1 minus 1, negative 2. Do that one more time. See it here. Negative 2 times 3 minus 6x. Negative 2 minus 1, negative 3, not negative 1. So you have to be very careful there with your negative exponents. We'll finish out these last two examples with fractions. Just to remind you, it means subtract 1. It means subtract the whole number 1 in the power rule. So 2/3 times 6 would be 4. X to the 2/3 minus 1, so minus 3/3 is negative 1/3. So 4x to the negative 1/3. Then we have negative 2 times 4 minus 8x. Negative 2 minus 1 is negative 3. F prime of x, 4x to the negative 1/3 times minus 8x to the negative third. Last one, putting it all together. What we have, negative 6x to the negative 1/2 plus 3x to the 1/2. Negative 1/2 times negative 6 is positive 3. X to the negative 1/2 minus 1 in the form of 2/2 is negative 3/2. So negative 3/2 plus 1/2 times 3, 3 over 2. X to the, this one's interesting, 1/2 minus 2/2, negative 1/2 to the negative 1/2. So as long as you remember, right, it seemed like it was going to be super easy, and then we start dealing with fractions and negatives, and it gets quite a bit harder. Key point here, to differentiate a polynomial term, multiply the term's coefficient by its exponent. And so if you're struggling with fractions, you're going to have to just work through that. You'll get there. And subtract 1 with the exponent. So if you need like in-depth explanations of the fractions or the negatives, just like quickly text me. I can give really good explanations of those. Don't get hung up on those for too long. All right, last two things here. Sometimes this will require rewriting. What I mean by that is, if we have f of x is 2 over x squared minus 4x to the third, you can't just like subtract this and make this 2 over x to the first minus 12x squared. That is not what this derivative is. It has to be in polynomial form. So there's a few changes you might make. If I were to do this one, all I need to do is remember this is the same thing as 2x to the negative second. That's what negative exponents are. They're regular exponents. Move them to the bottom to make them positive. Minus 4x to the third. And so now when we use the power rule, f prime of x, negative 2 times 2, negative 4x, subtract 1 is negative 3, not negative 1. Then we have minus 12x squared. Minus 12x squared. Notice that is not what we had if you just like tried to apply the power rule of denominators. So it has to be in polynomial form. Same thing here. What I would imagine some people might do is they might try and say, oh, this is 1 times 1 just to make 1 when we take those derivatives. But it's not. You have to multiply this out. You have to multiply this out to make x squared plus 5x plus 6. Then we can do the power rule to say f prime of x is 2x plus 5. Okay, so you have to multiply these things all out. The one that's really going to throw a lot of people for a loop here, yes, you do need to know your radical exponent, like fractional exponent rules. So 3x, this is about as hard as it's going to get. If we have this here, this would be 3x. I like to do this one step at a time. This is 3x, and I like to write f of x each time, over x to the 2/3. The denominator is the root number. The numerator is the number inside the radical like there. So it's 3x over 2/3. Then I like to always bring these up. I always just bring these up. I'd rather deal with negative exponents. This is 3x times x to the negative 2/3. And finally, our exponent rules, if we are multiplying, like x squared times x to the third, right? Remember x squared times x to the third, we would add those exponents to make x to the fifth. That applies even with these fractions. So this is 1 plus negative 2/3. This is x to the 1/3 power. All I've done there is rewrite. I haven't done anything besides rewrite here to get that this is the same thing as f of x equals x to the 1/3. Now I can power rule f prime of x is 1/3 x, right? 1/3 comes out front, multiplies by 1, x to the 1/3 minus 1, negative 2/3. If there's one thing calculus is going to make you, it's going to make you really good at working with fractional exponents and things like that, doing that mental math real quick in your head. Last example, it's going to keep us just under 20 minutes here. Oh yeah, sorry, key point, you have to be in polynomial form. You might have to distribute, you might have to divide, you might have to change exponents around, but you have to be in standard polynomial form before you apply the power rule. Last one, putting it all together, right? Putting it all together, this is straight from the delta math. Given f of x equals negative 3x squared plus 2x, find the slope of the tangent line. I'm going to do one better. We're going to find the whole equation of the tangent line when x is equal to 4. There's another assignment that does that. I just copied the wrong thing here. The equation of the tangent line. Whenever you see equation of the tangent line, the first thing you put on your paper is this. I need a point and I need a slope. I need a point and I need a slope. The point is easy. It's literally just where does f of 4 wind up. Negative 3 times 4 squared plus 2 times 4, just plugging in 4 here. Negative 3 times 16 plus 8, negative 48 plus 8, negative 40. So when x is 4, y is negative 40. So easy enough there. That's our point. The slope of the tangent line is the derivative. We need to find, first we find the derivative of the function. The derivative of the function 2 times negative 3 is negative 6. X to the reduce 1. You can write that x to the first. If that helps, that's fine. Then 2x to the first, 1 times 2 is plus 2, and the x to the first subtracting 1 makes x to the 0. Or you just remember this is a line. It's got a slope of 2. So here is our f prime. We plug in 4 to find the slope at the point we care about, which is when x is 4. What we have here is negative 24 plus 2. What we have here is a slope of negative 22. If you have a point and a slope, it is as easy as putting it into point-slope form. Y minus y1 equals the slope times x minus x1. Here it is, y plus 40, because minus negative 40, equals the slope, negative 22, times x minus 4. This is the equation of our tangent line. Point-slope form is fine. You could rewrite it in slope-intercept, but you don't have to. That is it. That is the equation of the line. Tangent to this curve